This is the arithmetic unit of my homebrew 8-bit CPU build. It currently can do addition and subtraction. It has two adder chips here, they're 4-bit each, together they form an 8-bit adder. And in the previous episode we've added this negation circuit down here, such that the adder can also do subtraction. And the way we built this 8-bit adder is there's two 4-bit adders, and the carry output of the first adder is connected to the carry input of the second adder. And this 8-bit adder has a carry input itself and a carry output itself. But we're currently throwing away the carry output. If we actually stored the carry output somewhere and we allowed subsequent addition or subtraction instructions to reuse the previous carry, we could chain more of these 8-bit adders together across multiple instructions to create wider additions. So instead of just adding more of these chips on the side to create 16, 24, 32-bit adders, we can do the same thing across multiple instructions, where a subsequent instruction can use the carry of the previous instruction. And so instead of unrolling the adders in space, by adding more of them, we can unroll them in time by taking multiple instructions to do the computation. And that's what I want to do today. I want to take the carry output, store it in a register somewhere, and then allow the next instruction to pick whether it wants to start with a fresh carry or reuse the carry we stored away from the previous operation. There's a lot of room here where we could put the register, but I have different plans for these locations. So let me add a breadboard to the top where we can place this carry register. Let me connect the power rails. I'm going to use one of these 74HC377 registers, which I've already used in the program counter and in the register file. And I'm going to be storing the carry flag in here. It's a very convenient register because it has a clock input, but it also has a clock enable. This allows us to always clock the register, so we're not messing with the clock signal, which is very annoying. But we can still pick whether the register should store a value by setting the clock enable appropriately. I think that's a good spot. Let me hook up power and ground. And I think we want to see what we're currently storing into the register as kind of the new carry flag, and what's coming out of the register as the current carry flag. So let me add two LEDs here such that we can look at that. Let me use a blue one for the next carry value that we're going to store into the register. And I'm going to use a red LED for the current state of the flag register. So let me connect the blue LED, the next carry flag, to the data input of the register. And the LED showing the current state of the carry flag register, let me wire that up to the data output of the register. Alright, there we go. So we have our carry flag register here. This is our input, what we're going to store in the next cycle. This is the current state of the carry flag. So now what we need to do is actually take the carry output of the adder down here and bring it up to this input of the carry flag register such that it gets preserved into the next cycle. Now in our current setup we have a subtraction control signal, which is all the yellow wires down here, which causes the right hand side to be inverted and also sets the carry input to a 1. And so this forces the carry input of the adder to be a 0 when we're doing addition and a 1 when we're doing subtraction. But now that we have this carry flag register here and we're preserving the previous instruction's carry output, we might actually want to pick whether we want to start with a fresh carry 0 or 1, or whether we want to reuse whatever's in the carry flag register up here. So there's 4 options. We can pick between addition and subtraction, and we can pick whether we want to start with a fresh carry or with the previous carry. And to make this selection, I'm going to use a 4-way multiplexer to provide a carry input value to the adder. This 74HC153 chip here is a 4-way multiplexer. We have already used this in the program counter to pick what the next value of the program counter is going to be. Is it just stepping through the program, or is it doing a jump? And it's going to be useful here as well. Connect power and ground. And now this multiplexer has 2 select inputs, which together form a 2-bit binary number, which pick one of the 4 inputs to be transported to the output. So let me add 2 LEDs such that we can observe what the current select lines of the multiplexer are. And I think we'll call this 2-bit value the carry operation. Bit 0 of this value here will go to pin 14 of the multiplexer, which is the select line A. And then bit number 1 will go to pin 2, which is the select line B of the multiplexer. All right, there we go. So that drives the select lines on the multiplexer, and we can observe the value, and we can conveniently bring some instruction bits over here to drive this value. Now I'm going to connect bit 0 of the carry operation to the subtraction control signal down here, such that whenever this last bit is 0, we're not inverting the input, and whenever this last bit is 1, we are inverting the input. That means all the even carry operations where this bit is 0 is going to be something that looks like addition, and every odd carry operation where this bit is 1 is going to be something that looks like subtraction. This multiplexer is going to pick the carry input for the adder, and so we want to connect the output of the multiplexer to the carry input here. And the carry input of the adder is currently connected to the subtraction control signal, but we no longer need this connection because we have a better way of picking the carry input. So let me remove this wire and actually connect the output of this multiplexer at pin 7 to the carry input of the adder here. And now we have 4 inputs here in the multiplexer, one for each option we can pick with the select signals here. Option 0, which is even, so that's an addition, we can make the plain old addition, where the carry input is just set to 0 and we start fresh. So that means we'll connect pin 6 of the multiplexer, option 0 to ground. And then option 1, which is odd, which is a subtraction where the right-hand side gets inverted. I think we'll make the plain old subtraction we had before, where the carry input is just forced to a 1, such that we get the 2's complement. So I'm going to connect pin number 5 here, the input for option 1, to VDD, such that we inject a 1 into the adder. Now option 2 is going to be another addition, and option 3 is going to be another subtraction. But for those, I don't think we want to set a constant carry value. For both of those, I think we just want to take whatever's in the carry flag register. So let me bring the current value of the carry flag register down here to this input and connect it to both inputs for option 3 and option 2. So the current value is up here, and we'll bring it down to the multiplexer. All right, I think that's all that's needed. We have a new carry flag register up here, some LEDs to show the current state of that. And we have this multiplexer here which picks a carry input for the adder. And instead of using the subtraction control signal directly as a carry input, we actually have this new carry operation here, a 2-bit value, which picks the carry input for the adder, but also controls the subtraction control signal. So this is almost like an ALU mode signal, which picks what mode the ALU is in. Let's give this a quick try to see if everything works. Let me power it up. Okay, nothing catches on fire. That's a good starting point. And the carry flag register comes up in a random value. It's currently at 1. Let's go clear that to 0. We have a clock enable signal here. The clock enable is an active low signal, so by setting it to 1, the clock should be disabled. So let's see if I can toggle the clock without anything happening. Okay, so that's the clock input. And me toggling it doesn't do anything. But if I instead set the clock enable input to 0, so it's enabled, let me toggle the clock again. And as you can see, we stored the 0 that's currently at the input of the flags register into the flags register. So that's working. First up, let's do an addition which will produce a carry output. Let's maybe add 128 and 128 because it's an easy number to wire up. So that's 128 on the left-hand side and 128 on the right-hand side. And as you can see, the output overflows back to 0 and the carry out is set. And up here at the flags register, you can see that the next value for the carry flag is going to be a 1. So if I toggle the clock at the flags register, we want to see that carry flag be stored in the register and displayed on this red LED here. And there you go, that's what happens. So let's try the 4 different carry operations we have here. Let me pick more sane input values, maybe 8 and 4. Let me set the carry operation to 0. So with the carry input set to 0, the right-hand side is not being inverted. It's just the 4 that we've set. And the carry input to the adder is a constant 0. And the output is what you would expect. It's 8 plus 4 equals 12. So that's the plain old addition. Let's try the other addition, that is carry operation 2. Now with carry operation 2, we would expect to see the current value of the carry flag up here to be presented to the adder as a carry input, but that doesn't seem to be working. And in fact, I forgot that the multiplexer has an output enable input here all the way at pin 1, and we have to pull that low to actually produce an output value. So let me do that. And there you go, now it's working. So we've picked carry operation 2, which is an addition, but this time we're taking the current state of the carry flag up here and we're presenting it to the adder as an input. And indeed, the output is no longer 12, but it is 13 because we're adding 8 and 4 plus the carry flag that's currently in the carry register. Now let's go and switch the carry flag to 0 such that we can do the same test for the subtraction. Conveniently, the current addition doesn't produce a carry, so if I toggle the clock of the carry register, we should see the current carry output here be stored in the carry register. And that works. The carry register is now at 0. And this is a good check. We're still in carry operation 2, so we're using the current carry register. And the current carry register is 0, and correspondingly the carry input of the adder is 0. So let me switch to carry operation 1, which is the plain old subtraction. So in operation 1, the subtraction control signal is set. So the right-hand side gets inverted, which is correct, which is what you can see here. And since it's operation 1, we're injecting a 1 into the carry input of the adder through this multiplexer. And that's what's happening here. And indeed, the 8 minus the 4 we've presented here is the 4 that you see as an output. Now let me switch this to carry operation 3. 3 is still a subtraction, so the subtraction control signal down here is enabled and the right hand side is still inverted, but now we're reusing the carry value in the carry register as the carry input for the adder. And so instead of injecting a fixed 1 into the subtraction, we're now taking this carry flag register, which is a 0, and injecting this into the addition. And now this time, the 8 minus the 4 we present at the input doesn't produce the 4 at the output that you would expect, but because the carry isn't set, it's actually a 3 at the output. So that's pretty cool. We now have this carry operation input here, which gives us 4 different modes that this arithmetic unit can operate in. Mode 0 is the plain old addition, where we just inject a 0 as the carry input for the addition. Mode 1 is the plain old subtraction, where we invert the right hand side and we inject a 1 into the carry input of the adder. Then mode 2 is an addition, but instead of injecting a fixed 0 into the adder carry input, we're picking the current carry register value. And then mode 3 is the same for subtraction. We are inverting the right hand side, but instead of injecting a fixed 1 as the carry input, we're using the current carry flag register value as the carry input. And then this register has an enable signal here, and it has a clock, and what it will do is it will store the carry output of the current instruction such that the next ALU instruction can make use of it and decide whether it wants to continue on with the addition, basically extending the bit width of the adder, or whether it wants to start with a fresh carry and basically start a fresh addition. So that's pretty cool. Let me power this down and then let's go integrate this into the CPU build. Alright, so this is my CPU build as I've left it. Let me bring back the ALU with the changes we just made. Okay, first things first, let me connect the power back up. This cable here comes from the read data port 1 on the register file, and this needs to go to the left-hand side input of the ALU. And the other cable is read data port 2. This needs to go to the right-hand side input of the ALU. And then this long cable here is the ALU result that connects back up to the ALU buffer, which allows us to write back the ALU result into the register file. So this needs to go to the result of the ALU. And then this yellow wire down here that is hooked all the way up to instruction bit 12, this used to be the subtraction control signal, but we've replaced this now with a 2-bit signal which actually controls the carry operation. So let me remove this wire and let me replace it with a 2-bit cable. And we're going to use bits 12 and 13 of the instruction to drive this carry operation control signal of the ALU. And since the ALU is now using a register to track the previous operation's carry bit, we need a clock to drive that register. Alright, so that's the clock of the register hooked up to the clock of our CPU. And we also have a clock enable signal here on the register. And that allows us to only update the carry flag stored in the register when we're actually doing an ALU operation. So for example, when we execute an ALU instruction, we want to store the carry output of that instruction in the carry flag. But if we then execute a jump or a move instruction, we don't want to destroy the information in the flags register. So we don't always want to enable this register. We only want to update it when we're actually doing an ALU operation, such that when there's other operations in between that don't affect the ALU, we don't want those to destroy the flags. And one way for us to do this is to actually connect the clock enable of the register to the output enable of the ALU buffer. If you recall, we used the ALU buffer to take the result of the ALU and drive it onto the register file write data port. And this is always enabled when we do an ALU operation and we actually want to take the result of the ALU operation and store it in a register. And so that enable line of the buffer here is a good indication that we've just executed an ALU instruction that has an interesting result, which we want to store into the register file. And that's going to be a good indication that whatever the ALU produce, we also want to store in the flags register. So let me take that enable signal of the ALU buffer here and bring it all the way up here to the flag register such that it can be enabled in that case as well. The enable is all the way in the upper right corner here, pin 1 of the register. Alright, so we have wires flying all the way across the CPU build right now. We're going to clean that up soon by moving some of the things onto dedicated PCBs where we can route the signals as actual PCB traces. And that will clean things up a bit, and it will allow us to focus on specific parts of the CPU while we're updating them and building them out. And all the other bits and pieces can be on the dedicated PCB without a lot of wiring mess to go with it. Alright, and that should be all that's needed. We have this carry operation control signal here, which controls which carry the ALU uses and whether it inverts the right-hand side for subtraction or not. We've wired up the clock and the clock enable of the flags register here, and we hook the left and right-hand side end result back up. So all that's left to do is to actually go take a look at our instruction set architecture, updated such that it makes use of these new control signals that we've wired up to instruction bits 12 and 13. Then update the assembler and write a new program that actually makes use of this carry functionality that we've just added. Let's go do that. First, we are going to update the instruction set architecture document because we're using more instruction bits now to control the ALU operation. In the previous episode, we have added this subtract control signal and we hooked it up to instruction bit 12. And lines 11 and 12 here correspond to that bit. It basically indicates that when we set bit 12 to 0, we're doing an add, and when we set bit 12 to a 1, we're doing a subtract. And with the changes we made today, we're also using bit number 13 of the instruction to decide what operation the ALU should perform. We now have 4 different options that the ALU supports. Bit 0 we have used to decide whether we invert the right-hand side or not. Whenever this bit is a 0, we're doing kind of an addition, and whenever this bit is 1, we're doing sort of a subtraction. And the way we hook this up in hardware is whenever bit 13 is a 0, we're doing the plain old addition and subtraction with the constant carry input, where the carry is a 0 when we do an add, or the carry is a 1 when we do a subtraction. So when this bit is 1, we're considering the carry flag when we do addition and subtraction. And this is generally known as an add with carry and a subtract with carry. Or also subtract with borrow, but I'm sticking with carry just to have fewer terms floating around. Alright, pretty cool. So these are the 4 operations we've already tested: regular add, regular subtract, add with carry, and subtract with carry. And now we can define corresponding new instructions. I'm going to copy the add and subtract instruction down here, and I'm going to set bit number 13 to 1 for the new copies. And these new instructions are going to be our add with carry and our subtract with carry. Alright, cool. That's all that changed in the instruction set architecture. We have 4 ALU operations now, which is pretty exciting. Let's add these instructions to the assembler so we can use them in programs. We have this test.s file that we've used to test the assembler. So let me add the add with carry and subtract with carry instructions here. I'm just going to use some random registers, or 2 or 3 or 4 or 5, because this isn't really a functional program, it's just for testing. Alright, and let me run this through the assembler and then let's see what breaks. Alright, the assembler doesn't know what an add with carry is. So let's go change that. Let me open the assembler source file and let's go add the new instructions. Okay, there we go. So the first problem is in instruction parsing. So in the parse instruction function here, if I scroll down a bit, here's the parsing code for the regular add and subtract instructions, and we'll want to copy those for the new instructions. add with carry, and subtract with carry. We're going to need new opcodes for this. We also need support for printing the instructions back out. Printing is going to look exactly the same as the regular add and subtract. And last but not least, we need to update the encoding of the instructions such that the assembler can actually produce a binary output. So this here is how we encoded the add and subtract instruction. And here we set bit number 12 to either a 0 or a 1, depending on whether we wanted an add or a subtract. But after today's changes, we're now also looking at bit number 13 of the instruction to decide what the ALU is doing. So starting at bit number 12, we're going to encode the ALU operation as a 2-bit number now. And the regular add is just 0, 0, and the regular subtract is just 0, 1. But now we also have the add with carry and subtract with carry flavors, and these have the upper bit set to a 1. Okay, that should be it. The assembler should now support add with carry and subtract with carry. Let's give that a try. Okay, that worked, and we see a binary output. Let me print the instructions back out. And if I scroll up a bit, you can see the instructions encoded here. We have an add and a subtract, which are encoded with ALU op 0 and 1. And we also have the add with carry and subtract with carry, which are encoded with the ALU operation 2 and 3. Okay, let's write a new test program that makes use of these new instructions. Let's call it something like test carry, because we're testing the carry flag. Let me copy the code that clears the registers to 0 from the subtraction test program. And let me add 2 knobs. These will make it easy to identify the different parts of the program once we're running it on the actual CPU. With this carry flag and the new operations that use it, our CPU is now able to compute wider addition and subtraction than just the 8 bits that its registers have. So let's try to do 24-bit addition, which uses 3 registers to store one of the numbers and 3 registers to store the other number. We can add maybe 10 million and 6 million and see if we can actually get the 16 million we would expect. Let me convert this to hexadecimal numbers because that's going to make it easy to know what we need to load into each of the registers. So 10 million in hexadecimal is 98, 96, 80. 6 million is 5B, 8D, 80. And 16 million is F4, 24, 00. The convenient thing about hexadecimal notation is that pairs of digits tell us what we need to load into the individual registers. Because each hexadecimal digit corresponds to 4 bits in binary, 2 hexadecimal digits corresponds to 8 bits in binary, which also corresponds to the size of our registers. So in our case, we want to load register R0 with the value hex 80, R1 with hex 96, and R2 with hex 98. Let me also write down the binary representation. That's going to make it easy when we test the thing. And then down here, when we're done loading R0, 1, and 2, the concatenation of all the bits in R2, R1, and R0, so the entire 24-bit value, should correspond to the decimal value 10 million. Now let's do the same for the value 6 million. Let's load that maybe into registers R4, R5, and R6. And then again, looking at the hexadecimal representation, we need to load R4 with the hex value 80, R5 with the hex value 8D, and R6 with the hex value 5B. Let me again take note of what the binary representation is. And again, at this point, the concatenation of all the bits in R6, R5, and R4, the 24-bit value, should correspond to the decimal number 6 million. Okay, R0, 1, and 2 contain 10 million, R4, 5, and 6 contain 6 million, so let's do the addition, and let's see whether we can get the 16 million out of that. We're going to start with the least significant bits in register R0 and R4, and we're just going to add them. So this will take the value in R4 and add it to the value in R0 and then store the entire result in R0. And in this case, R0 is 128 and R4 is also 128. And when we add those together, the addition is going to overflow. So we expect R0 to be set to 0, but the carry flag to be set. And now next up, we want to add the middle 8 bits of the numbers. But we don't want to just use the plain old add instruction. We actually want to use the new add with carry instruction. Because the addition of the previous 8 bits, the lower 8 bits, it overflowed and produced a carry flag. And this carry flag we want to factor into these middle 8 bits. So we're going to add with carry the value in R5 to the value in R1. And I'm going to store the result in R1. And let me quickly compute what the binary value here is going to be. So those were the middle 8 bits. Now we want to compute the upper 8 bits of the result. And so we're going to use an add with carry again. We're going to add the value in R6 to the value in R2 and then store the result in R2. And let me again quickly compute what we want to see as a result here. And at this point, the concatenation of the registers R2, R1, and R0, the entire 24 bits, should correspond to the decimal number 16 million. That's addition. Let's see if we can do the same thing for subtraction. Let's use the 16 million we already have in registers R0, 1, and 2, and let's maybe try to subtract 800,000 from that. So we'd expect to see 16 million minus 800,000 equals 15,200,000. And again, let me convert this to hexadecimal so it's easier to know what should go into the individual 8-bit registers. 60 million I can steal from above, and then 800,000 in hexadecimal is 0C3500, and 15,200,000 is E7EF00. And you can get those values pretty quickly if you use Python or some advanced calculator. The 60 million we already have as a result from the previous addition, so what's left to do is to load the 800,000 into registers. Let's use our 4, 5, and 6 again. And let me note the binary representation again. And again, at this point, the concatenation of the bits in R6, R5, and R4, the 24-bit value, should represent the decimal value 800,000. So R0, 1, and 2 contain 16 million, and R4, 5, and 6 contain 800,000. So let's do the subtraction. We'll start at the lower 8 bits again, and we'll just use a regular subtraction to start this off. So we're subtracting the value in R4 from the value in R0, and then we're storing everything into R0. Then to compute the middle 8 bits, we'll want to use a subtract with carry, because the subtraction in the lower 8 bits produces a carry output that we need to consider for the middle 8 bits. So we're going to subtract the value in R5 from the value in R1, considering the carry, and then we'll store the result in R1. And then the upper 8 bits, we'll do another subtract with carry, and we'll subtract the value in R6 from the value in R2, considering the carry, and then store the result in R2. Let me again note what the binary values should be. So 15,200,000 in the lower 8 bits is just going to be 0. The middle 8 bits are going to be hex EF, and the upper 8 bits is going to be E7. And so again, at this point, the concatenation of the bits in R2, R1, and R0, the 24-bit value that this gives you, should be the decimal value 15,200,000. And so this is the basic recipe to do wide addition and wide subtraction on a CPU that has a carry flag. For the lowest bits, you start out with a plain old add or subtract that doesn't consider the current state of the carry flag. But for all the upper bits, you're using add with carry or subtract with carry to consider whether the previous addition or subtraction, the one for the lower bits, produces a carry output that you need to consider and carry along in your addition. So at this point, we should have seen a successful 24-bit addition and a successful 24-bit subtraction. Another nice test would be to see if we can do the Fibonacci sequence forwards and backwards, but on 16-bit values instead of just the 8-bit values. Let me add a few NOP instructions as a separator, and then let me clear the register file back to 0. I think register R3 has been unused, so that still contains a 0, so let me just use R3 to fill in all the other registers. Alright, so that should give us back a cleared register file. Let's start by doing the Fibonacci sequence forward in 16 bits. And so the biggest Fibonacci numbers that we could fit into 8 bits were 233 and 144. So let's maybe start at those. Let me load 233 into register R0, such that R0, R1 is going to be one of our 16-bit values. And 144, let me load that into register R2, such that R2, R3 is going to be the other 16-bit value. And then we're going to do a 16-bit addition of the value in R0, R1 to the value in R2, R3. And we're going to store the result in R2, R3. So as before, we're going to use a regular add for the lowest 8 bits, and then an add with carry for the upper bits. Let me add a comment what the resulting binary value is going to be. And so at this point, the concatenation of R3 and R2 should be the next Fibonacci number, which is 377. Then we're going to compute the next number, but we're going to flip the registers around. We're going to take the value in R2, R3, and we're going to add it to the value in R0, R1, and then store everything into R0, R1. Let me also compute the binary result. And so at this point, the registers R1, R0 should contain the decimal number 610, which is the next Fibonacci number. Okay, let me do this for the next pair of numbers. So this is going to be Fibonacci number 987. This one is going to be 1597. Let's maybe do another pair. This is going to be the number 2584. And this is going to be the number 4181. And we could keep going. I think there's another 6 or so Fibonacci numbers that will fit into 16 bits. But I think what we have here is enough to showcase that we have 16-bit addition with the carry flag here. Let's turn this around. Let's do the Fibonacci sequence backwards in 16 bits. But let's maybe start at the two biggest Fibonacci numbers that we can fit into 16 bits. And that's going to be the value 46,368. Let me load that into R0, R1. And the value 28,657. Let me load that into R2, R3. All right, and then let's do 16-bit subtractions. We're going to take the value in R2, R3, and we're going to subtract it from the value in R0, R1, and then store the result in R0, R1. And again, we'll use regular subtract for the lowest 8 bits, and then subtract with carry for all the upper bits. Let me note the binary pattern again. At this point, in registers R1 and R0, we should see the next lower Fibonacci number show up, which is 17,711. Let's do the same thing again, but swap the registers around. This time we're taking the value in R0, R1, which is the 17,000 here, and we're subtracting it from the value in R2, R3, which is the 28,000 something here. And at this point, we expect to see the next lower Fibonacci number, which is 10,946. Let's do another pair of those. Next number is 6,765. Next number is 4,181. Let's do another pair, which is going to give us the Fibonacci numbers 2,584 and 1,597. And at this point, I think we can just halt the processor. All right, this is pretty cool. So to recap, we clear the registers. We do a 24-bit addition on two numbers, 10 million and 6 million, and we check whether we see 16 million as a result. Then we do subtraction on 24-bit numbers. We take 16 million and subtract 800,000, and then check if we get 15,200,000 as a result. Then we clear the registers again. We compute 6 Fibonacci numbers starting at 233 and 144, but this time in 16 bits. And then we're doing the Fibonacci sequence backwards. We're starting at 46,000 and something and 28,000 and something, and we're computing 6 numbers backwards in the Fibonacci sequence, and then we're stopping the CPU. Let's see if the assembler is happy with our program. And indeed, it looks happy. Here's the binary output, which is the actual instructions that our CPU can run. But if I scroll up, we can see a printout of the program that we've provided, clearing the registers, 24-bit addition, 24-bit subtraction, clearing the registers again, Fibonacci sequence forwards in 16 bits, and Fibonacci sequence backwards in 16 bits, and then we're going to halt. Pretty nice. Let me use the makefile to get the binary output for this, which also works. Pretty cool. Let's write this to the program memory and then power up the CPU and step through the program and see if this actually works on the real hardware. Cool, let's give this a test. Alright, so that's the new program stored here in the program memory. Let me power this up and then let's step through the program and check if everything works. Let me step it out of reset. First up, we're going to do the usual clearing of the registers. So that's the load immediate followed by the moves that clears the register file. Now we have two NOP instructions to separate it from the interesting bit. Let me step over those. First up, we're going to test addition with 24-bit numbers. We're going to add the number 10 million to the number 6 million, and we expect to see 16 million as a result. So first up, we're going to load the number 10 million into register R0, R1, R2. R0 is going to hold the lowest bits, R1 the middle bits, and then R2 the upper bits of that 24-bit number. So let's execute the 3 load immediates. So first up, R0 gets hex value 80. R1 gets hex value 96, and R2 gets hex value 98. And together that forms the decimal number 10 million. Then we're going to load the number 6 million into register R4, R5, and R6. First up, R4 gets the hex value 80, R5 gets the hex value 8D, and R6 gets the hex value 5B. And together that forms the decimal number 6 million. Okay, so we have two 24-bit numbers. One is in R0 to R2, and the other one is down here in R4 to R6. And now we're going to do wide addition. We're going to take the value in R4, 5, and 6, and we're going to add it to the value in R0, 1, and 2. And we start with the low bits. We're adding the value in R4 to the value in R0. And as you can see, this is a regular add instruction as we had before. And correspondingly, we have the carry operation of the ALU set to 0, which is a regular add operation. And that add operation has a 0 as the carry input. Coincidentally, both register R0 and R4, the two registers we're adding, both contain the value 128, which is basically just the top bit set. And as you can see over here at the ALU, we're adding 128 to 128, which is 256, which overflows the 8-bit adder and goes back to 0, and the carry output is set. And this carry output is transported up here to the carry flag register. And since we have the ALU buffer enabled, because we're doing an ALU operation, the carry register is enabled here as well. And what should happen when I hit the clock is that this input carry flag here should be stored here in the register and displayed on the red LED. Cool, that's exactly what happened. And as you can see, the 0 result, because of the overflow, is stored in register R0. Next up, we are taking the value in R5 and we're adding it to the value in R1. But this time, it's not a regular add operation, it's an add with carry operation. And you can also see this at the carry operation input of the ALU. This is no longer 0, which was the regular add, it's 2, which is the add with carry. And because this is an add with carry, we're actually using the current value in the carry flag register as the carry input for the adder. So the previous add overflowed, and what we're doing now is we're considering that overflow in this addition here, and we're basically continuing on the carry chain and continuing the addition. And again, since the values are pretty large, the output again overflows and produces a carry flag. And this carry flag gets presented here at the register. And again, since we're doing an ALU operation and the ALU buffer is enabled, this register is going to be enabled as well. And then this carry input is going to be stored in the carry flag register for use in subsequent instructions. All right, so that stored the result here in R1. Now we're at the final add instruction of our full 24-bit addition. This time we're adding the value in R6 to the value in register R2. And again, it's an add with carry, so the carry operation here is set to 2, which is the add with carry. And again, we're taking the value of the carry flag register, and we're using that as a carry input. And we're doing the addition, and this time the addition actually fits into 8 bits, so we're not producing an output carry. As you can see up here at the carry flag, we're presenting that 0 carry output as the next value to be stored in the carry flag register. And since this is an ALU operation and the ALU buffer is enabled, this register is also going to be enabled. So what we'll see is that 0 carry flag is going to be stored in the carry register. And the result of the addition here is going to be stored in register R2. All right, there you go. The result has been stored in R2. And as you can also see, the carry flag register here was updated. And we finished the 24-bit addition. Register R0, 1, and 2 now contains the result value, which is indeed the number 16 million, the result of adding 10 million to 6 million. And since these numbers were fairly big, they required 24 binary bits to represent, we actually had to split addition up into multiple separate instructions. The first instruction was a regular add to basically start the whole process, but then afterwards we kept using add with carries to add the higher bits of the number. And that allowed us to do a 24-bit addition on just an 8-bit adder by basically feeding the addition piecemeal through the adder circuit and by making use of the flags register to take the carry and carry it over into the subsequent additions. So that's pretty sweet. Next up, we're going to try subtraction on 24-bit numbers. This time we're taking the 16 million we have here, and then we're subtracting the number 800,000. And we'd expect to see 15,200,000 as a result. So first up, we're going to load the number 800,000 into registers R4, 5, and 6 down here. As a first step, R4 will be set to the value 0. R5 gets the hex value 35, and R6 gets the hex value 0C. And now we're going to subtract the 24-bit number in registers R4 to 6 from the 24-bit number in registers R0 to 2 up here. And again, we're starting out at the lowest bits. We're subtracting the value in R4 from the value in R0. And this is a regular subtract operation. And as you can see over here, the carry operation input of the adder is set to 1, which indicates a regular subtraction. The regular subtraction means we're just using a fixed 1 input for the carry input, and we're also enabling the inversion of the right-hand side. So this basically computes the 2's complement of the right-hand side before feeding it into the adder. And it's a pretty simple operation. Both of these registers are 0, so basically we're computing 0 minus 0. And as you can see, the result is indeed 0, and the carry output is set to 1, which is a side effect of using this 2's complement notation. And that 1 carry output gets presented here to the register, and when I toggle the clock, this 1 is going to be stored into the carry flag register. All right, that worked, and the 0 result got stored into R0. Now we're doing the next subtraction. We're subtracting the value in R5 from the value in R1. But this time it's not a regular subtraction, it's a subtract with carry. And indeed over here at the ALU you can see that the carry operation is set to the number 3. 3 indicates subtraction with carry. And this time we're not feeding a constant 1 to the carry input, but we're actually using the current state of the carry flag as a carry input to the adder. And because it's a subtraction, we're still inverting the right-hand side to get the 2's complement. What's interesting with this subtraction right now is that we're actually not producing a carry output. So we're presenting a 0 to the carry flags register. And when I hit the clock, that 0 is going to be stored in the flag register here. All right, perfect. So the result got stored into register R1. And as you can see, the flags register is now a 0. Now to the final subtraction, we're subtracting the value in R6 from the value in R2. And again, it's a subtract with carry. So over here at the ALU, you can see that the carry operation is set to subtract with carry. And this time around, you can actually see that the carry input is no longer 1. Instead of injecting a fixed 1 like we do for regular subtraction, we're just using whatever's in the carry flag up here. And the carry flag happens to be a 0, so we're actually injecting a 0 as the carry input for the add here. And so let me execute this subtraction, which means the result of it is going to be stored in register R2. That worked, and you can see in registers R0, 1, and 2, we now have the value 15,200,000 spread across the 24 bits afforded by these 3 registers. All right, pretty cool. So that was a 24-bit addition and a 24-bit subtraction enabled by this new carry flag register up here and the new carry operation selection signals here in the ALU, which allow us to do regular addition and subtraction or addition and subtraction considering the value in the carry flags register. The next 2 operations are NOPs to separate this from the next part of the program. And one thing that is interesting is the carry flags register is currently set to a 1, but the adder is not doing any real addition. It's just adding 0 and 0 and produces a 0 as an output. And as a side effect of that, the carry output is a 0. So we're presenting a 0 to the carry flags register. But the next instruction is not an ALU operation. It's a NOP operation. And as you can see, the ALU buffer is disabled, so we're not using the ALU result to store anything into the register. And we're taking this as a cue to indicate to the register here to not update itself, such that when we execute the NOP instruction, we're not inadvertently destroying the value that's currently in the flags register, because we want that to be preserved up to the next ALU operation. So let me step over this one NOP, and what you should be able to see is this carry flag here should not change. And there you go. that stayed the same. We're still presenting a 0 to the carry flag register, but the register refuses to update because this is not an ALU operation and the register update is disabled. Another knob, let me step over that. And now we're doing some 16-bit Fibonacci sequence computations. But first up, we're going to clear the register again. We're just using the value in R3 here to populate the rest of the register file with zeros. This time around, we're starting at the largest Fibonacci numbers we can fit into 8 bits, which is 233 and 144. And we're using those as seed values to compute the next higher numbers, those that actually require 16 bits to represent. So first up, we're loading the value 233 into R0. And we're loading the number 144 into R2. And at this point, the registers R0 and R1 contain the 16-bit value 233, and registers R2 and R3 contain the 16-bit value 144. And so as a first step, we're taking the value in R0, R1, and we're adding it to the value in R2, R3. And we're doing this with two separate additions, one to add the lower bits and one to add the upper bits. The first one for the lower bits is going to add the value in R0 to the value in R2 with a regular add operation. And the result gets stored here in R2. And then the next instruction is an add with carry, as we did before, because we want to do a wide addition. And this time we're taking the value in R1 and we're adding it to the value in R3. But this time it's an add with carry. As you can see over here, add with carry mode is selected on the ALU, which means the carry output of the last addition, which was a 1, is now used as the carry input for this addition here. And as you can see, both registers contain the value 0, so we're technically adding 0 plus 0 because 233 and 144 both fit into 8 bits, so the upper 8 bits are all zeros. But since the addition of the lower bits that we have just executed produced a carry output, we're actually now using this carry output and feed it into the addition. And so the result of the addition of these upper 8 bits is actually a 1 because the addition in the lower 8 bits overflowed and produced a carry, which now makes the upper 8 bits increment by 1. So let me toggle the clock, which is going to store this 1 result here in register R3. And pretty sweet, that worked. We added 233 plus 144, which produced the result 377 here in registers R2 and R3. And 377 actually doesn't fit into 8 bits anymore. We need 16 bits to represent this number. And you can see this here. It's no longer just the lower 8 bits that contain a value, but the upper 8 bits also contain a non-zero value. And so next up, we are going to take this 377, which is here in R2, R3, and we're going to add it to the 233, which is up here in R0, R1. And again, we're using a regular add to do the lower bits of the addition. And we're using an add with carry to do the upper bits of the addition. And as a result, registers R0, R1 now contain the value 610, which is indeed 377 plus 233. Next up, we're going to add 377 to 610, which gives us 987 in registers R2 and R3 here. Then we're going to add 987 to the 610 up here, which gives us the value 1597 in R0, R1. That we're going to add to the 987 down here, which gives us the value 2584 in registers R2, R3. That we're going to add to the 1597 we have here in R0, R1, which gives us the value 4181 here in R0, R1. Which are indeed the next Fibonacci sequence numbers after 233 and 144. So that seems to be working. Let's do the whole thing backwards. Let's start at the largest 16-bit Fibonacci numbers we can represent, and let's count backwards using subtraction. So we're going to load the number 46,368 into R0, R1. And we're going to load 28,657 into R2, R3. And now we're running the Fibonacci sequence backwards using subtraction. We're starting by subtracting 28,657 from 46,368, which produces the value 17,711 in R0 and R1. Next up, we expect to see 10,946 down here in register R2 and R3. Then we're going to subtract that 10,946 from 17,711. And the result is 6,765 that appears here in R0, R1. Next number is 4,181 in R2, R3 down here. 2,584 in R0, R1. And another one. We get the number 1,597 here in R2, R3. And those last few numbers we have already seen when we counted forwards using addition. So that seems to work, and those were the correct values of that part of the Fibonacci sequence. And that concludes our test program. We're all the way at the end at the halt instruction, and the CPU just stops here. So this is pretty exciting. The CPU now stores a carry flag that is produced by the adder. We have a new multiplexer here, which allows an instruction to pick whether it wants a fixed 0 or 1 to be used as the carry input for the adder, or whether the previous ALU operations carry output should be used instead. This allows us to chain multiple 8-bit addition and subtraction instructions together so they operate on more bits. For example, we had an addition with 24-bit numbers, and we used 16-bit addition and subtraction to run the Fibonacci sequence forward and backwards beyond what we were able just with 8 bits. And storing information about an ALU result in a flags register is a pretty common technique in older CISC processors. It's very useful to carry information between instructions without needing an explicit register operand or dedicated encoding bits for it. I'm pretty sure we'll make good use of this carry flag in the future, and we'll probably also add a few more flags to the processor. As a next step, I think we want to give our CPU the ability to shift the bits in a register around, and that will unlock a few very useful operations that we can do with it. That's something for the next time though. Thanks a lot for watching. Like and subscribe if you want to see more of this, and see you next time.